from Dante Lauretta from the University of Arizona, who's going to talk about OSIRIS-REx touch and go sample acquisition event and the implications for the nature of the return sample. So Dante, please take it away.
Thank you. Can you bring my slides up, please? Excellent. Okay, so OSIRIS-REx has successfully completed its entire mission to asteroid Bennu, and we're anxiously looking forward to beginning our return cruise phase to get these samples back to the Earth. We arrived at the asteroid in late 2018, and we spent the majority of 2019 surveying the asteroid, initially globally, identifying multiple regions of interest as potential sample sites, and then selecting our site, and on October 20th, 2020, successfully contacting the asteroid surface and collecting material. I won't go into a lot of the details about the global characterization campaign, but I will point out that we had a special issue of Science in November of 2020, 3 papers in Science and 3 in Science Advances that cover some of the highlights from our campaign and what we have learned. Next slide, please. So this animation shows you the approach to sample acquisition. So we're coming in on the left side. That orange line is the OSIRIS-REx spacecraft trajectory. At about 125 meters above the surface, we fire thrusters at a location we call the checkpoint, which begins the descent towards the asteroid surface. And then at about 55 meters, we fire thrusters again to match the surface velocity, making a brief contact to collect the sample, and then firing once again the back away thrusters to leave the surface of the asteroid. And so let's take a look at what happened during that event. As Makoto mentioned before me, the ruggedness of the Ryugu's surface was a real surprise and a challenge to their sampling. Bennu gave us the same challenge, a rough and rugged rocky surface, very different than what we expected. Next chart, please. So we had to upgrade the spacecraft guidance system. We launched with the capability of targeting a spot within 25 meters of a chosen location on the surface. There were no such locations on Bennu that were within the safety requirements of the spacecraft. So we switched to an optical onboard autonomous guidance system called natural feature tracking, which also served as a hazard avoidance software. And the diagram that you can see on the right of this slide is the hazard map for our chosen sample site called Nightingale in a 20-meter diameter crater in the northern regions of asteroid Bennu. With the natural feature tracking system, we were able to contact within 73 centimeters of our targeted location, which is phenomenal engineering performance and exceeded all of our expectations and resulted in safe contact and successful sample collection. Next chart, please. So how did we do? One of the big success criteria of the mission is to bring back 60 grams of bulk sample, as well as contacting the surface with small contact pads to collect fine grain material from the optically active area. So this image on the right here shows you a view from our SAMCAM instrument. That white semicircle at the bottom there is half of the sample collection mechanism. And so that's what we place onto the surface of the asteroid. And then there's a faint blue circle that shows the region where we actually made contact. The device is capable of ingesting particles up to 2 centimeters in longest dimension. And we counted 35 particles that met that size criteria that are likely to be collected and in the sample chamber right now. We did extensive lab testing with the TAGSAM device against a variety of regolith conditions, primarily looking at various particle size frequency distributions. Given the conditions that we assessed at the surface of Bennu at the time of sample collection, that algorithm would predict that we collected between 258 and 575 grams of sample, depending on the mobility or the inertia of the material, which translates most directly to the particle density. So of the 60-gram requirement. Next chart. Then we take a look at the contact with the surface. So now you can more fully see the TAGSAM device, including a portion of the robotic arm. The part that's wrapped in that black blanketing is the gas bottle. So the sample collection works by pressing that filter, the TAGSAM head, into the surface, and then opening up one of 3 bottles of high purity nitrogen gas, which fluidizes the regolith and blows it into the collection chamber. So these 2 images were taken about 1 second apart, and it's right before contact and right after contact before we fired the gas. So we're truly looking at the mechanical interaction of the spacecraft with the asteroid surface. And everything looks fantastic here in terms of how we wanted the experiment to proceed. We made a nice flush contact with the surface. There was no large obstruction that was causing the sample head to tilt, and we could comply up to 15 degrees of tilt with the asteroid surface. We went in the half a second or so between contact and gas firing. We went in about 4.5 centimeters, I should say, before the second image was taken. So the surface was really soft and compliant. Really looks like our models where we run discrete element simulations with very, very low cohesion between the particles, which was a surprise to us. We weren't sure what that cohesive value would be. And so we also see right when we liberate the gas that there's a dust cloud. We also see in post sampling checkouts that there is obscuration on the optics, anywhere from 20% transmission up to 60% transmission, depending on the lens that we're looking at. So excellent conditions for the sampling event, exactly the kind of surface interaction we were hoping for. Next chart, please. And then we fire the gas bottle, and you can see an extensive amount of material being mobilized by TAGSAM. The text over there on the left kind of walks you through the timeline of our duration on the surface. So contact was sensed by the spacecraft's accelerometer, and we experienced a surface force of about 10 newtons, which is very, very low, and again, consistent with a compliant surface and very low intergranular cohesion. 1 second after that signal, the gas bottle was opened up and the agitation started, and we let that experiment proceed for 5 seconds. So 6 seconds after contact, we initiated the back-away thrusters. We contacted the surface with a velocity of 10 centimeters per second. At the time of the back-away burn, we were still moving forward at 4 centimeters per second, so we still had a substantial forward velocity. That deceleration was entirely due to the TAGSAM gas. There was no restoring or return force from the surface to the spacecraft. It took us another 3 seconds to stop moving forward, so we penetrated over 48 centimeters down into the asteroid surface. At 9 seconds, we reached 0 velocity and then started the back away. And 16.6 seconds after initial contact is when the TAGSAM head rose above the altitude where the original surface was. As we'll see later on, we actually cratered. And so we were inside the TAGSAM impact crater at that point. Next chart. So everything went really great. We think we collected a lot of material. That was on October 20th. 2 days later, on the 22nd, we took this series of images and a whole host of other images of this nature. We saw that we did, in fact, do very well, that we collected a lot of material. And in fact, we did too well. And there were several large stones that were propping open the check valve. There was a flap that was designed to close behind the sample as it entered the collection chamber. That was wedged open in 5 distinct locations, causing a substantial amount of material to be lost from the head. In these sequences of images right here, we estimate about 10 grams of sample is lost. Through our subsequent analysis, we estimate we lost over 60 grams of sample in between the collection event and or these images specifically and the stow. So almost our entire mission requirement was lost into space. Next chart. So we had to use visual confirmation to come up with an estimate of how much mass was in the sample head. We had a different experiment planned called the moment of inertia technique, which involved spinning the spacecraft around with the TAGSAM arm extended well away from the rotation axis. We realized that that would exacerbate the mass loss problem, and we would actually lose more material by trying to measure the mass. So we relied simply on the visual confirmation. We saw that the screen was blocked and opaque to light. We estimated that would require about 57 grams of sample. We saw those 5 large particles that were causing the mass loss in the first place. We estimate that those had a mass of about 28 grams. And then where it was propped open, we could see sample inside the head. And we estimated there was another about 300 grams of material. I should say that we had to assume a density, of course, for all of these measurements. We assumed 1,800 kilograms per cubic meter for the bulk particles, and for the visible regolith, 1,200 kilograms per cubic meter. So we estimated about 400 grams of observable sample in that period right after sample collection. Next chart. And as I mentioned, we think we lost about 60 grams. So we're estimating there's probably 250 or 300 grams of sample that's coming home. We're very excited. It's an excellent sample, well in excess of the 60 grams. You can see some of the images of the TAGSAM base plate here. There's abundant fine grained material sticking to those contact pads. Particles up to 4 millimeters across are visible. And there's a lot of dust just all over the surfaces of the TAGSAM. Based on our spectral data of the asteroid's surface, we're very excited about the return sample. It contains abundant water in the form of hydrated silicate clay minerals, carbonates, magnetite, which is an iron oxide, and a host of organic material. Basically exactly the kind of sample we were hoping to bring back from Bennu, mineralogically and chemically speaking. We feel like we have inside that TAGSAM head. Next chart. So after we resolved all of that, and we were confident we had abundant sample, we were able to place that sample head into the return capsule. And that little movie that I showed you there was after we severed the tubes, the gas tubes and the bolts from the head and the arm, placed it inside the return capsule and tucked it away, getting ready for its 2.5-year journey home. Next chart. So these two images, there's two slides here. If you could kind of blink them back and forth to show the before and after images. So the first image was taken in 2019 in March as part of our initial global survey. That's
you have 5 minutes left.
Thank you. That's the Nightingale site inside that 20-meter crater. And then you can see in the second image, which was taken just 12 days ago on April 7th, where we have visibly disturbed the surface. There is a crater at the tag point, which is right about in the center of that the original impact crater there. We estimate it has a diameter of about 8 meters. So we're excited to go look at our scaling laws. We know the energy that we put into the surface there and see if that's consistent with our predictions of the asteroid surface. Large boulders up to over 1 meter in diameter were moved, some of them up to 12 meters away from the contact point. And there's substantial other evidence of surface disturbance, including a darkening and reddening of the material, which is exciting because that's what we predict the most pristine unspace weathered material looks like on Bennu. So a great, successful final look at the asteroid. We're now gearing up for our departure, which is scheduled for May 10th. That's a change from the original plan. We had originally planned to leave the asteroid early in March, but we found this trajectory a little bit later. It actually preserves 50 meters per second of delta V, and there's still a backup departure available on May 24th, and we come home on the same date of September 24th, 2023. So we are looking at extended mission opportunities, just like the Hayabusa 2 team, but we have not settled on a design. And our next major activity is the Earth return, September 24th, 2023, when the pieces of Bennu will be back on Earth, and we can begin the final science campaign of looking at Bennu underneath the microscope. Thank you for your attention.
Great. Thank you very much indeed. So I see a couple of questions in the chat. I'm not sure if I see everything, but I have a question from Amara Graps. Is there evidence that Bennu has a dual regolith porosity? So, for example, more porous on the top layer and then less porous underneath, for example?
It's hard to tell from the data from the TAG event because the forces after we fired the gas were driven entirely by the gas interaction with the regolith, and we could see that the head was moving around a little bit and particles were impacting it. So we fluidized and expanded the regolith after that first second of contact. So any physical state of the sample, the regolith is not discernible. We are obviously doing a lot of work in that first second where we saw the contact of the head, and we have the accelerometer, high rate accelerometer data to try to understand the state of the regolith at the surface. Otherwise, we're relying on radio science and gravity field estimates. And we do see an underdense equator in those solutions, but they're non-unique. And there's a lot of challenge to try to interpret asteroid interior structures just from gravity field data alone.
That's great, thanks. And then one other question that I see in the chat, which was, were there any initial compositional analysis performed by the instruments on the spacecraft?
All the compositional data comes from either visible and near-infrared spectroscopy. We look at 0.4 to 4.3 microns. We see the 2.7 micron absorption, which is characteristic of phyllosilicate minerals, and lots of information at the 3.4 micron region, which is a combination of carbonates and organics. We also have a thermal emission spectrometer, which confirms the phyllosilicate detection and also is where we see the strong magnetite signal. And that's all just of the surface of the asteroid, not specifically the collected sample.
That's great, thanks. And then there's one final question, which is how surprising is the depth of penetration, so almost 50 centimeters? And is it something you can estimate ahead of interacting with these rubble piles?
It was very surprising. And I can tell you, and Patrick Michel, who's on here, also remembers, we did a lot of studies asking the team to try to tell me how deep we thought the head would penetrate. And I got answers from 3 millimeters to 3 meters. So basically everything was possible. And now we have the actual answer. So we're going back to all those models and we're figuring out the ones that got it right and what properties of the regolith did we assume in those cases. And now we could better predict the next time we sample Bennu how deep we'll penetrate.
That's great. Thank you very much indeed for the presentation, for the answers. Very much appreciated.